So today we're gonna learn about a topic entitled concrete road or rigid pavement. Types of pavements. There are two types of pavements based on design considerations. The first type is the flexible pavement. It is consists of a mixture of asphaltic or bituminous material and aggregates placed on a bed of compacted granular material of appropriate quality in layers over the subgrade. Another type is the rigid pavement. It is constructed from cement concrete or reinforced concrete slabs. Grouted concrete roads are in the category of semi-rigid pavements. The main difference between flexible and rigid pavement is based on the manner in which the loads are distributed to the subgrade. The concrete road definition. Concrete road is also known as the rigid pavement. These are roads having their wearing surface consisting of cement concrete. It is either plain or reinforced. These roads are types of rigid pavements and remain in serviceable condition under all with weather conditions. Thus, concrete roads are also considered as all-weather roads due to their excellent riding surface, pleasing appearance, and long life under most severe traffic conditions. Cement concrete roads are much preferred. Cement concrete roads are superior to most other types of roads, including bituminous roads. These roads are very popular as high-cost pavements in developed countries like America, Russia, Japan, and other countries. The types of rigid pavements. The first type is the jointed plain concrete pavement, or the JPCP. This does not use any reinforcing steel and is constructed with closely spaced contraction joints. It has a joint spacing of 5 meters to 10 meters. Jointed reinforced concrete pavement or JRCP is where the reinforcing steel is placed at mid-height and discontinued at the joints. Dowel bars are required for load transfer. Joint spacing is increased to 10 meters to 30 meters. The third type is the continuously reinforced concrete pavement or CRCP. This method is very costly and complete elimination of joints are achieved by reinforcement. And the last type that is very uncommon is the pre-stressed concrete pavement or PCP. This comprises new and innovative construction methods. The structure of rigid pavement. The structure of a rigid pavement consists of the following layers: the concrete slab or surface course, the granular base or stabilized base course, the granular subbase or stabilized subbase course, the frost protection layer, which is optional, and the subgrade soil. So here is a typical rigid pavement structure figure. This is the concrete pavement, this, the base course, the subbase course, and the subgrade or the existing soil. The advantages of concrete road construction. The first advantage is that concrete roads have long life than any other roads. Second is that these roads are durable and are practically unaffected by weathering agencies. Third is that they provide an excellent riding surface under all weather conditions. They provide an impervious, dustless, and sanitary surface, and they do not develop corrugations. Sixth advantage is that these roads can be laid on any subgrade. It can also be easily reinforced when they are to resist high stresses due to heavy wheel loads of the traffic. Concrete roads are non-slippery and offer less destructive resistance. They provide a good visibility for traffic during night hours. And finally, the maintenance cost is low. The disadvantages of concrete road construction. The first one is that the initial cost of concrete road is high. They are liable to crack and warp due to temperature variations. They become noisy under iron-tired traffic. Skilled supervision and labor are required for construction. Less resilient than bituminous or WBM roads. It requires long time for curing and thus cannot be opened to traffic earlier. And it is very difficult to locate and repair sewers and water mains lying under the pavement in their case. The materials used in concrete roads. The, the Portland cement concrete commonly used for rigid pavements consists of Portland cement, coarse aggregate, fine aggregate, and water. Steel reinforcing rods may or may not be used. It depends on the type of the pavement being constructed. So let's talk about the first material, the Portland cement. Most highways agencies use either the ASTM specifications or the ASTM designation C150 or the AASHTO specifications or AASHTO designation M985 for specifying Portland cement quality requirements used in their projects. So there are basically five types of concrete. The first type is the type 1. It is suitable for general concrete construction, where there are no special properties required for the concrete. The second is the type 2. It is suitable for use in general concrete construction, where the concrete will be exposed to moderate action of sulfate or where moderate heat of hydration is required. Type 3 is suitable for concrete construction that requires a high concrete strength in a relatively short time. It is sometimes referred to as high early strength cement. Type 4 is suitable for projects where low heat of hydration is necessary. And lastly, Type 5. It is used in concrete construction projects where the concrete will be exposed to high sulfate action. Another material is the coarse aggregates. The coarse aggregates used in Portland cement concrete are inert materials that do not react with cement and usually comprised of crushed gravel, stone, or blast furnace slag. The material is well graded with the maximum size specified. Materials retained in number 4 sieve is considered coarse, coarse aggregate. The qualities of coarse aggregates. First is that coarse aggregates must be clean, so this is achieved by specifying the maximum percentage of deleterious substances allowed in the material. Other qualities is the ability of the aggregates to resist abrasion determined by Los Angeles abrasion machine test and the soundness test. Another material is the fine aggregates. Sand is mainly used as the fine aggregate in Portland cement concrete. The specifications for this material usually include the grading requirements, soundness, and cleanliness. So the grading requirements for this is normally adopted by the state highway agencies. The soundness requirement is usually given in the terms of the maximum permitted loss in the material after 5 alternate cycles of wetting and drying in the soundness test. And cleanliness is often specified in terms of the maximum amounts of different types of the deleterious materials contained in fine aggregates. The most important material is water. So water used in mixing or curing of concrete shall be clean and free from injurious amounts of oil, salt, acid, vegetable matter, or other substances harmful to the finished concrete. So the main water requirement is stipulated is that the water used also should be suitable for drinking. It requires that the quantity of organic matter, oil, acids, and alkalis should not be greater than the allowable amount in drinking water. The last material that is optional is the steel reinforcing bars. Steel reinforcing bars may be used in concrete pavements, first, to reduce the amount of cracking that occurs, second is as a load transfer mechanism at joints, and third as a means of tying two slabs together. So, first, steel reinforcement used to control cracking is usually referred to as the temperature steel. The steel rods used as load transfer mechanism at joints are known as dowel bars. They provide flexural, shearing, and bearing resistance. They have much larger diameter than the wires used in temperature steel, while those used to connect two slabs or pavements together are known as tie bars. They should be either deformed bars or should contain hooks to facilitate the bonding of the two sections of the concrete pavement with the bar, usually have much smaller in diameter than the dowel bars, and are spaced at larger centers. Joints in concrete pavements. Different types of joints are placed in concrete pavements to limit the stresses induced by temperature changes and to facilitate proper bonding of two adjacent sections of pavements when there is a time lapse between their construction. These joints can be divided into four basic categories. The first is expansion joints. They are usually placed transversely at regular intervals to provide adequate space for the slab to expand. That's why it's called expansion joints. Another is the contraction joints. They are placed transversely at regular interval across the width of the pavement to release some of the tensile stresses that are so induced. The third one is the hinge joints. They are used mainly to reduce cracking along the center line of highway pavements. And lastly, the construction joints. They are placed transversely across the pavement width to provide suitable transition between concrete laid at different times. Stresses in rigid pavements. Stresses are developed in rigid pavements as a result of several factors, including the action of the traffic wheel loads, the expansion and contraction of the concrete due to temperature changes, yielding of the subbase or subgrade supporting the concrete pavement, and volumetric changes. These different factors that can induce stress in concrete pavement have made the theoretical determination of stresses rather complex, requiring the following simplifying assumptions. The first assumption is that concrete pavement slabs are considered as unreinforced concrete beams. Any contribution made to the flexural strength by the inclusion of reinforcing steel is neglected. The combination of flexural and direct tensile stresses will inevitably result in transverse and longitudinal cracks. The provision The provision of suitable crack control in the form of joints, however, controls the occurrence of these cracks, thereby maintaining the beam action of large sections of the pavement. The third assumption is that the supporting subbase and/or the subgrade layer act as an elastic material in that it deflects at the application of the traffic load and recovers at the removal of the load. Stress induced by bending. So figure 20.5 shows the deformation of a beam on an elastic foundation. The stresses developed in the beam may be analyzed by assuming that a reactive pressure P, which is proportional to the deflection, is developed as a result of the applied load. This pressure is given as P is equal to Ky, where P is the reactive pressure at any point beneath the beam, Y is the deflection at the point, and K is the modulus of subgrade reaction. The modulus of subgrade reaction is the stress that will cause an inch deflection of the underlying soil. So this equation assumes that K is constant, which implies that the subgrade is elastic. However, this assumption is valid only for a limited range of different factors. Research has shown that the value of K depends on the certain soil characteristics such as density, moisture, soil texture, and other factors that influence the strength of the soils. K is the value of particular soil will also vary with the size of the loaded area and the amount of deflection. The modulus of subgrade reaction is directly proportional to the loaded area and inversely proportional to the deflection. In pavement design, however, minor changes in K do not have significant impact on design results, and an average value usually is assumed. The plate bearing test is commonly used for determining the value of K in the field. A general relationship between the moment and radius of curvature of a beam is given as 1 over r is equal to m over ei, where r is the radius of the curvature, m is the moment of the beam, e is the modulus of elasticity, and I is the moment of inertia. The general differential equation relating the moment at any section of a beam with the deflection at a given section is given as this equation, whereas the basic differential equation for the deflection in an elastic foundation is given as this equation. The basic differential equation for a slab is given as m sub x equals this equation, or m sub y is equal to this equation. H is the thickness of the slab, mu is the Poisson's ratio of concrete, W is the deflection of the slab at a given point, m sub x is the bending moment at a point about the x-axis, and m sub y is the bending moment at a point about the y-axis. The term in the previous equation is called as the stiffness of the beam, whereas the stiffness of the slab is given by the term within the brackets of this equation. So this is the stiffness of the slab. This term is usually denoted as D, where D is this equation. In developing expressions for the stresses in a concrete pavement, Westergaard made use of the radius of relative stiffness, which depends on the stiffness of the slab and the modulus of subgrade reaction of the soil. It is given as this equation, where this is the radius of relative stiffness, E sub c is the modulus of elasticity of the concrete pavement, h is the thickness of the pavement, mu is the Poisson's ratio of the concrete pavement, and K is the modulus of subgrade reaction. The design considerations for concrete pavements. The design consideration factors considered in the AASHTO procedure are presented in the 1999 guide, and this includes the pavement performance, subgrade strength, traffic, concrete properties, drainage, and reliability. The design considerations are the basic factors considered in the PCA, or the Portland Cement Association design methods, includes the following: flexural strength of the concrete, subgrade and subbase support, and the traffic load. The pavement conditions and defects. First is the surface defects, which includes the wear and polishing, map cracking, pop-outs, scaling, shallow reinforcing, spalling, and spalling. Another one is the joints. These defects includes the longitudinal joint defect and the transverse joints defect. The third is the pavement cracks. This includes the transverse lap cracks, the decracking, the corner cracks, the minder cracks. The pavement deformation. This includes the blow-ups, faulting, pavement settlement or heave, and utility repairs, patches, and potholes. So the pavement road ratings. This is how we should rate the roads. So ratings are related to needed maintenance or repair. For rating 9 and 10, new pavements or recent concrete rehabilitation, this means that no maintenance is required. For rating 7 and 8, first signs of wear, scaling, or cracking, this needs routine maintenance. For ratings 5 and 6, first signs of corner cracks, faulting, and joint or crack spalling, this requires surface repairs, sealing, or partial depth patching. For ratings 3 and 4, moderate to severe faulting, multiple slab cracking, and joint failure. This requires extensive slab or joint rehabilitation. And for ratings 1 and 2, this is where pavement failure requires complete reconstruction. So basically, that's all that you need to learn about concrete roads. So it is then. Thanks for watching.